Okay, so welcome everyone to Toronto Data Workshop. I'm representing Rohan today. He just got called away, but he'll be back, so we'll see him before the end. I'm really happy to introduce our two speakers today, Sana Shams and Waris Bhatia, both from the University of British Columbia. They'll be talking to us about accessible investigative journalism, navigating Canada's largest corpus of government documents using AI. Sana is a research fellow through UBC's Data Science for Social Good program. She's currently pursuing a Bachelor of Science in Cognitive Systems with a minor in data science and is passionate about the intersection of technological development and ethical compliance, particularly in the fields of data science and machine learning. Waris is a data science intern with the UBC's Data Science Institute. He's a senior undergraduate studying computer science at UBC. I'll just tell you a bit about the data set that they'll be talking about today. Open by default is a data set from the Investigative Journalism Foundation, which is Canada's largest collection of government documents, over 4.5 million pages of access to information and privacy requests and corresponding government documentation. So the project that we're going to hear about it has enhanced data capture through optical character recognition, improved search performance using large language model vectorization and topic modeling to reveal the high-level subject matter represented in this data set. And the final development of the project was a Retrieval Augmented Generation RAG LLM pipeline, which enables a chatbot to provide tailored context-rich responses to user queries paired with follow-up research directions. So I'm really happy to welcome our two speakers, and I'll let you take it away. And sorry, as we go through, if you have questions, pop them in the chat, and we'll take them up at the end.
Thank you so much, Kelly, for your introduction. So yeah, as already mentioned, our project is accessible investigative journalism, and we've spent the last few months this summer developing some data science and natural language processing solutions to help improve the navigation of Canada's largest corpus of government documents. So first of all, a little bit about the Data Science for Social Good program. It is an interdisciplinary summer research program that brings together both graduate level and undergraduate students, and it's hosted by the Data Science Institute at the University of British Columbia, as well as various sponsors every year, such as data providers, domain experts, and other organizations like CFAR, the Canadian Institute for Advanced Research. And the overall objective of the Data Science for Social Good program is to essentially leverage interdisciplinary perspectives to apply data-driven solutions for social good. So one unique thing about the program is the students don't all come from a computer science background, and the cohort is quite diverse. We found that this is very helpful when trying to apply like social solutions and have cultural context and awareness. So our project partner for this summer was the Investigative Journalism Foundation, which focuses on public interest journalism with the purpose of strengthening democracy by driving transparent, data-driven reports. And a defining feature of the IJF is their publicly available databases, which cover key topics such as lobbying data, political donations, financial reports. And on top of hosting this information, the IJF doesn't want to just stop there. They're actually very committed to improving its accessibility so that the general public is also able to easily navigate and benefit from the information in these databases. For our project specifically, we'll be focusing on the Open by Default database, which is composed of all of the request statements that are sent by Canadians to the Canadian government under the Access to Information and Privacy Act. With over 4 million pages and counting, it is currently Canada's largest corpus of publicly available government documents. So it acts as a strong mechanism for driving transparency with the government. Each of the requests represents a request for information that is sent to the government by investigative journalists, civil rights lawyers, legal scholars, or just like the average Canadian citizen who is seeking information beyond what is available to the public. And the way that OBD is structured, on their website, if you open the database, each entry consists of a request statement submitted to the government, such as the one shown here. And then these requests can range from seeking informal email transcripts to official contracts, and really anything in between. And these requests are then paired with the documentation that is returned by the government. Although the OBD database hosts an abundance of valuable information with millions and millions of pages, there are several challenges that limit its accessibility and value as a tool, not only for the IJF journalists, but the general public who is trying to view the information on the database. The first and one of the biggest challenges is poor data capture. So for a lot of the documents that are in the database, they're actually non-native PDFs. And this means that they're essentially scans of physical documents that exist within government archives, but because they're non-native and they have to be scanned from a physical copy, we don't have access to the embedded text compared to digital-born PDFs that are digitally created. So it's much easier to record and parse the text. This results in poor data capture because of blurry scans. Maybe the document was crooked, maybe it has handwriting, and so on. And while these documents, even on a human level, it can be quite readable for us when we're looking at the scans, it has very poor machine readability. In addition to the poor data capture, another challenge that the OBD database faces is search quality, which is restricted by the IJF's current methods, which is essentially keyword search. And the way that keyword search works is it looks for the exact keyword, then tries to match the keywords used in the user queries to retrieve the relevant results. And essentially, the results are just going to be looking at which documents have a higher density and prominence of those keywords. So the more a word shows up in that document, the higher it'll be ranked for relevance. But unfortunately, this fails to consider the intent and the context of the question. So here in this slide, I have an example of what that problem would look like, where we have, let's say a user wants to learn about Indigenous people's inclusion in Canadian pension plans. So if they enter the keywords Indigenous and Canadian pension, unfortunately, the results that is returned, as you can see on the slide, is about addressing tuberculosis in Saskatchewan First Nations. It doesn't have anything to do with Canadian pension plans. And the reason for that being that this document probably has the highest density of the keywords in isolation, but not contextually used together. So this leads us to our problem statement, which is making meaning from a mountain of text. And Waris will take over.
Thank you, Sada, for the great introduction. So for our problem statement, the overarching goal of our project was to improve data capture and essentially make the OBD dataset easily searchable and navigable. So we wanted to make the OBD dataset more accessible to a wider range of users. So this includes people who come from a non-political and a non-journalism background as well. And we, as you'll see in this presentation, we employed some data-driven tools to improve accessibility of the data set. Next slide, please. So our project objectives, they broadly entailed improving data capture to extract more meaning from the original documents. Then we focus on enhancing the search performance for improving information retrieval. And then finally, also enabling user interaction, which essentially entails talking to the data set. So here's an overview of our timeline for the project. So the first step consisted of optical character recognition, or OCR, which essentially refers to extracting text from PDF documents. And we moved on to constructing a vector database, which would enable semantic search and also allow us to index and search efficiently. And then our next step consisted of topic modeling, where we extracted themes to classify document metadata. And we also envisioned to include advanced search, which was combining semantic search and some traditional querying methods that Sana just talked about. And then finally, we focused on our RAG LLM, or Retrieval Augmented Generation, coupled with a large language model pipeline, which is where you essentially enable a user to speak with the data set. So this is essentially what we envision the speaking with the OBD database part to look like. And as you can see, a user can input a question, and we would expect a response such as this one to be generated by the LLM. So in this slide, we see what policies were implemented related to COVID-19 in correctional facilities, and the LLM generates a response using the RAG technique. So next, we will touch on some of the specific methodologies that we covered in our project this summer. So first, we started with optical character recognition, or OCR, which essentially involves using pre-trained machine learning models that allow computers to read scans of documents and extract the text within them. So unfortunately, it's not a one-size-fits-all kind of situation. So you have to address poor data extraction that can come with a specific method. So currently, before we started working on this project, the IGF was using an open source model called Tesseract to conduct OCR. And our goal was to sort of improve on that by experimenting with traditional OCR services from Amazon as well as Microsoft, as well as use some large language models in our experimentation. So this includes Claude as well as GPT to perform OCR. So our OCR experiment results, we saw that Amazon's OCR service called Amazon Tesseract was better, where we were able to capture 40% less non-real words. This means less typos and incorrectly extracted words. Then we also saw that we were able to obtain 31% more words. So it identified and extracted more text. And then finally, we also saw improved extraction quality when we manually saw some of the tables, blurry scans, as well as documents containing handwriting.
Moving on with the text that is extracted by our OCR methodology, we started to build a vector database. So for those of you who aren't familiar with it, vectorization is the process of converting text data into numerical representations so that they can be processed by machine learning models. And the goal when vectorizing the text into numerical formats is that the numbers preserve the semantic meaning of the text. To do this, we employed embeddings, which are a form of vectorization that represents the numerical representation of words or phrases where semantically similar words are mapped nearby in the embedding space, as you can see in the diagram on this slide. To achieve this, we used transformer-based embeddings, which understand and represent the words within the context of the whole sentence or the chunk of text given, whether that be a paragraph or a page. These models are ideal for vectorizing entire documents and representing the words within the context that they were used, rather than having an isolated vector for individual words, so that we can avoid the issues, for example, with the search example, where Indigenous pension plans returned something about Indigenous tuberculosis documentation. Finally, the vectorization of the OBD dataset converts the text data into a form that our computers are going to be able to understand. And these vectors are necessary for later steps in our project, including topic modeling and labeling, semantic search, and the building of our Retrieval Augmented Generation large language model pipeline. To summarize our process, we analyzed a few different transformer models, each of which have their own advantages. And we were mindful of the size of the transformer models as well to balance performance with computational efficiency, given that our data was over 4 million pages of text. And the models that we tried ranged from encoder-only models such as BERT and DistilBERT and MPNet, all of which are very basic and foundational. And these models are used for tasks that are involved in understanding and encoding the text. But we also tried some end-to-end transformer models like FLAN T5 base, which can encode the text and generate new text on top of that. As mentioned, each of these models have their distinct advantages, some of them being known for their multilingual processing abilities, and others being known for having a really large context window so they can process very long documents at a time. To evaluate the embeddings quality that was generated by the different transformer models, we'll be looking at both some qualitative and quantitative metrics. So to start off with the qualitative metrics that we evaluated, first we started with looking at UMAP plots, which are essentially visualizations that reduce and plot the embeddings generated by the transformer models into 2 dimensions. And this is really important because originally some of the dimensions of the transformer models embeddings can go up to 700 plus, which is not super interpretable on an intuitive level for humans. And so these UMAP plots served as an initial impression of the potential topic clusters that are being represented by the embeddings, and we use it to scope things out. Additionally, we will also examine the most representative words for each of the clusters and topics, as well as the most representative documents for each cluster and topic. In terms of quantitative evaluations, we developed a pipeline that uses semantic coherence, which is a measure for how strongly interrelated the words or documents are within a topic cluster. Semantic exclusivity, which is how semantically unique the topics are from each cluster compared to the others, and also density-based clustering validation, which essentially measures the cohesion, separation, and noise of the clusters based on the densities in the embedding space. So given that these vectors contribute to the foundation of our project, it's really important that we pick the embedding model that best captures the meaning of our text in an efficient manner. Like mentioned before, an intuitive way to understand this as humans is through visualizing the embeddings. When plotting the embeddings in a 2D representation, such as the one shown here, we should expect to see clustering and dense blobs when a model has successfully captured the meaning of our text data, which represents distinct topics. So this means that semantically similar texts are clustered together and semantically different texts are quite distinct in the embedding space. Here's a dummy representation, but in reality, the representations are not going to be as clean as you will see in the next few slides. So actually, what we did to scope things out before trying it on our full database is we made a manually created database where we looked at texts that were from the following organizations represented in the OBD database. We made sure that the organizations were quite distinct in terms of the subject matter that they represented. So we have finance, the space agency, national defense, Health Canada, and law enforcement. And taking that curated data, manually created database, we pass it through our transformer models to visualize the UMAP plots generated. On the right, you can see Google FLAN T5 bases embeddings, and you can see that it wasn't super good at capturing the semantic meaning of the text, as the text from the different organizations are overlapped and there's not very distinct clusters. But on the left, you can see BGE M3, which actually ended up being one of our best performing transformer models in that it was able to accurately represent the different topic clusters, and they were, for the most part, pretty distinct.
So overall, based on these evaluations, we decided that our best performing model was BGE M3. BGE M3 also has key features such as being able to handle multilingual text, and it also has a large context window. So we vectorized the entire corpus of OBD using BGE M3, which was then stored in a PG vector database, which is essentially a Postgres database with the vector extension enabled. And here we have an example of what a tuple that exists in our vector database looks like. For each file, we separated the text content into smaller chunks of 1024 tokens, which roughly translates to about a page of text. So for each entry, we store the document number or the file ID. Then we also have a chunk ID, which is associated with the smaller chunks. Then we also have the text data in the chunk, and then finally the embedding for the text chunk. So overall, this would then enable us as a user to query the vector database using semantic search, where we can essentially input a keyword or a phrase, which is then transformed into a vector and then matched to our pre-built index of documents. So the matching is done based on essentially how similar or close together two vectors are, which is measured using cosine distance. And then finally, this allows a user to retrieve a desired number of documents from the database using semantic search based on how similar a chunk is to the user's query. So here we have a short demo of the vector search. So here you can see what the vector search looks like on our app, where you can input a query such as this and pick a number of search results that you would like. You can also filter based on the date range. And when you click submit, you would be able to see top 20 sources that match the context, the semantic context of the query. Then we can also play around by filtering it based on the organizations as shown on the IGF's front end. So if you pick the atomic energy organization here, you would see the results pertain particularly to that organization.
All right, so given the embeddings of the full OBD database by our selected transformer model, we moved on to applying topic modeling to the documents. Because our data set is quite large and diverse, as well as being unlabeled, topic modeling was an ideal approach for us to synthesize the meaning from the text, where we can extract the topics of the content being discussed in the OBD documents. So topic modeling is a method that's used to discover semantic patterns that are portrayed by a text corpus and automatically identify some high-level topics that exist within the database by returning summary sets of key terms derived by the text documents. The process uses statistical modeling and that leverages unsupervised machine learning to analyze and identify clusters of groups of similar words within a body of text. And it can be used to also identify the most prominent topic in a set of text/cluster, as well as secondary and tertiary level relevant documents. So essentially, topic modeling allows us to generate more intuitive document labeling, where documents will be assigned to topic tags that reflect the high-level topics that are represented in the text. This allows us to have more nuanced descriptions of the OBD dataset. As mentioned earlier, our database separates each document into smaller chunks of text, and these chunks are 1024 tokens in size, which allows us to get chunk-level topic labels, and these can be further aggregated to get document-level topic labels and ultimately like database-level topic representations. This will also allow us to enable topic search, where documents can be filtered by their topic tag. So here's a visualization of how a file's content is originally displayed on the left and what it would look like with topic labels and chunk level topic assignments on the right. This just makes it easier for the user to find the relevant information that they're looking for, rather than having to parse the entire document, which can sometimes go up for hundreds of pages. The topic model that we use for our project is BERT topic, which uses transformer-based embeddings like BGEM3 that we use to capture the semantic meaning of the documents. It then reduces the dimensionality with UMAP, and it clusters the documents and extracts topics by identifying representative words for each cluster. Using these representative words, we can generate topic labels through two different methods. The first one is by automating the process by using the OpenAI API to get GPT-4o Mini to assign a topic label when it's given the representative list of keywords by our topic model. And then the second option is to present the representative words to the editorial team of our project sponsor, the Investigative Journalism Foundation, to come up with representative topic labels given their domain expertise. So in the red box over here, you can see the topic words that would be generated by our topic model to describe a cluster. And then here is the label generated by OpenAI, and it's quite descriptive. So it's definitely helpful to reduce some manual labor. When evaluating the different configurations of our topic models, we examined the coherence score primarily, which measures how semantically consistent the top words in a topic are with each other. A high coherence score indicates that the words in a topic are closely related in meaning and context, making the topic easier to interpret and more meaningful. Here, we used an elbow plot to see how coherence score changes as we increase the number of topics being generated by our BERT topic model. And for this particular sample of text, we can determine that the best performing number of topics is around 90, as that's where the coherence performance plateaus. Using our final topic model, we can assign topic labels to each text chunk as stored in our PG vector database. And with the final set of topic label tags, we can also enable topic level search where documents tagged with search topics are returned. And while we didn't get the chance to implement this by the end of our term with the DSSG, the search mechanism should return the exact chunks within the document that have been tagged with the search topic, as one document can have several different topic tags across all of its text chunks.
So moving on to our final deliverable of our project, it was the Retrieval Augmented Generation Large Language Model pipeline, or a RAG LLM pipeline. So what is RAG? What is a RAG LLM? So traditionally, LLMs, they're generally just machine learning models that are capable of understanding and generating text. So for example, OpenAI's GPT-4 is a LLM which is trained on large sets of data, and it can perform various natural language processing tasks. We can enhance the response of these LLMs using RAG, which is a technique that consists of retrieving relevant context of the questions being asked using vector search. So what are some of the benefits of this approach over just using a traditional LLM? First of all, we see that we can retrieve up-to-date and accurate responses. So this will provide us with up-to-date information from the OBD database rather than just using information from when the LLM was trained. Second, it also helps mitigate domain knowledge gaps. We can retrieve very specific information within OBD that is only accessible through the ATIP Act. And then finally, it also helps reduce hallucinations, which refers to when LLMs produce factually incorrect or fabricated information. So this will help avoid misinterpretations due to overfitting or training data bias, as well as other high model complexities. So here is an example of what the RAG LLM pipeline looks like. Here we see that a user inputs a query, which is then converted using our selected transformer model, which would be BGEM3 in this case. This then goes on to conducting semantic search on our vector database and retrieving the context from the question. And then the relevant context is fed into our large language model using a prompt that is specifically engineered to our task. And then the LLM would generate a response for the user. So this bare bones RAG LLM pipeline, we can also make a few improvements to it by using a few simple techniques. So all three of these enhancements, they rely on making a new independent call to an LLM. So first, for example, we can use a query augmentation approach where we ask the LLM to rewrite and improve on the initial user query before searching the database. Similarly, we can also re-rank the results based on the context before they're sent to the LLM for generating response. And then finally, we can also edit the LLM's response, checking for readability and appropriateness so that it is suitable for the end user. And this is what the enhanced RAG LLM pipeline would look like diagram on a diagram. So it is important that all three additions involve a new prompt to an LLM. So as you can see, first we modify the user query with the query augmentation approach. Then we re-rank the retrieve results using a re-ranker. And then finally, here we see that we're editing the initial LLM response using a response editor LLM. And this allows us to access a lot of powerful features. So as you can see, some of the features that we can get from here involve natural language queries, question answering, document summarization, document comparison, jargon explanation, and also a conversational chatbot experience. So our project, it has a specific focus on question answering aspect of it. This contributes back to the project goals of OBD, which was to enhance search performance as well as enable user interactions. And here is a short demo of what the RAG LLM would look like. So a user can input a question again. This is, at this point, retrieving information from the vector database. And then we get a response using OpenAI's GPT-4o Mini. And this effectively answers the question, provides any caveats and suggestions for further questioning. And you can also see that it also shows us the documents that are referenced here. And if you click on the hyperlink, it takes you to the IGF's website for the document particularly, and also shows the top 10 sources that were retrieved. So now moving on to the evaluation of the RAG aspect of the pipeline. Some steps we undertook were involved developing a sample set of queries taken from the IGF staff and reporters. Then we fed these queries to the basic RAG pipeline to generate a response, and then we scored these responses. And it's important to note that the scoring is inherently subjective, and there's no gold standard for that. One method that we employed in this step was to use an automated Python library called ragas. And as you can see, ragas, it's a library that provides metrics to evaluate RAG, given the prompt, context, response, and ground truth. So first, it tries to answer the answer relevance part of it. So this essentially involves how relevant the answer is to the prompt. And we want to make sure that our RAG LLM answers the prompt and it's not random. Then it also looks at faithfulness, which is essentially answering the question, does the answer provide align with retrieved context? Then we look at context recall, which specifically focuses on the retrieval aspect of the RAG LLM. So we see if the RAG LLM retrieves all the information required to answer the question. And then finally, the aspect critique, it measures the level of harmfulness, bias, conciseness, and understandability.
All right, so moving on to the future directions and recommendations that we have for our project. The first one is to improve the reliability of our RAG LLM, specifically using some safety guardrails. So first of all, with using safety classifications, we can implement a prompt guard for malicious user instructions, which are designed to override the safety and security standards that the investigative journalism would like to uphold. So we can do this by applying fine-tuned models that were trained specifically to detect harmful user inputs, as well as detect the type of hazard they present. And on the slides, you can see the list of the different hazards that are classified here. In the case that a user inputs a harmful query, such as over here, what's a good way to harm animals? Our model should be able to identify that, first of all, this is unsafe, and then furthermore, classify the type of hazard category that is in the user query. And also just stop the RAG LLM from generating a response altogether. The next recommendation that we have for the IGF is to supplement their current search methodology of traditional keyword search with the vector semantic search that we have implemented onto their front end. So with traditional keyword search, as we mentioned before, ranking is based on the density of exact matches, whereas on the other hand, our vector semantic search will allow for the use of cosine distance of the search query to help add some contextual insight. And to do this, we recommend they use hybrid search. So we don't say throw away the traditional keyword search altogether, but with hybrid search, we are able to combine the strengths of both of these methods by merging keywords and vector search results. Basically, it identifies results that are both directly and contextually relevant to the user's query, while ideally minimizing the misses and irrelevant suggestions. And this framework should work in a similar format to our RAG LLM pipeline. However, instead of just delivering the results from semantic search with our vector database, we'll also compare the results from the raw text data where the keyword density is maximized in the documents. And we'll feed both of the results into our large language model to help synthesize a useful response for our user. Moreover, our project has just been focused on applying this framework to the Open by Default database, but the IGF has a wide array of other databases as shown here, and they're still releasing more as we speak. So we envision that our work can be extended to the other databases, especially political donations and lobbying databases. This would really be helpful in capturing the semantic meaning and efficiently retrieving more appropriate documents, as well as identifying any hidden relationships, particularly among political donors or lobbying efforts.
So just to summarize our work, over the past 4 months, we started with improving text recognition of the PDFs in the OBD database, which contains more than 4 million pages currently. Then we constructed a vector database and implemented search on the database using semantic context. Then we also performed topic modeling to generate tags and labels for the documents. And then finally, we built a RAG LLM pipeline, which first searches the vector database and then generates a response for the user's query. So overall, we envision that through the collaboration between the Data Science for Social Good program and the Investigative Journalism Foundation, our project makes the OBD database more accessible and easier to use. Ultimately, our work intends to increase transparency and promote accountability of Canadian government organizations and representatives. We also hope that our project benefited IGF and their mission to strengthen Canada's democracy by driving transparent, data-driven reporting. And then finally, we hope that it helped improve accessibility to OBD data so that it's not only for journalists, but for everyone to use. Thank you so much for listening to our presentation, everyone. And if you have any questions, feel free to pop them in the chat or unmute your mic and ask.
Wonderful. Thank you so much. What a fascinating project. What a great experience and so much impact as well. I'm just going to stop the recording now so we can start the questions and people will be able to have a very free and open conversation. So I'll stop now and say thank you again.